BM25 found the right passage but buried it below keyword-heavy hits. You'll see how to connect the pieces into a workflow that scores query passage pairs and re-ranks a retrieved shortlist. I'm Professor Pi, teaching search and IR with simple Python. Re-ranking is what you reach for when a fast lexical retriever like BM25 returns useful passages but buries the best one under noisy, keyword-stuffed results. People rely on a neural re-ranker when the very top results must be right. Think question answering or enterprise search, where a single paragraph needs to surface first. MonoT5 turns relevance into a text-to-text decision, so a transformer can directly answer a tiny relevance question. It's more expensive than BM25, so we run it only on a short candidate list. Here's the basic flow. Run a cheap retriever to get a shortlist. Then have a seek-to-seek model read each query and passage and answer a relevance prompt. The decoder's preference between label tokens becomes our score. Stronger preference, higher rank. We'll build a small, readable example that walks the whole path. It purposely creates a wrong first stage order, loads a pre-trained MonoT5 re-ranker, scores a single pair, scores a batch, and computes a tiny evaluation number that shows the user pain when the right passage is buried. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we simulate the retrieval failure by making a tiny shortlist with the relevant passage not at the top. This snippet creates a tiny retrieved shortlist where the relevant passage starts at rank 3. The first stage order is intentionally plausible for a lexical retriever. P2 repeats high-frequency query words, while P1 contains the clinically useful evidence in more natural language. The variable order represents the candidate list we will re-rank, and docs keeps the passages short enough to inspect on screen. The printed rank makes the failure mode explicit before any neural model enters the picture. The output shows P1 is present but buried, which is exactly the re-ranking opportunity. Next, we load the MonoT5 model and the tokenizer, so the re-ranker can score text-to-text preferences. This example loads Castorini MonoT5 base MS Marco using the Hugging Face Objects AutoTokenizer and AutoModel for Seek-to-Seek LM. MonoT5 is a sequence-to-sequence re-ranker, so the ranking signal comes from the decoder's preference for label tokens rather than from an embedding dot product. The code calls talk.encode to get token IDs for the label words true and false, which are the two labels we will compare at scoring time. Model.eval is used to freeze training behavior and disable dropout so inference is stable. The printed output shows the concrete label IDs that will anchor every later score. With the model in memory, we score one query passage pair and inspect how the model prefers true or false. This code scores a single query and passage by formatting a short relevance prompt and converting it to tensors with talk. The prompt function puts query and passage into the text the model expects. Then talk prepares input IDs and attention mask so the model can run. Instead of full generation, we read the first decoder step logits and pick the positions corresponding to the true and false label IDs we encoded earlier. Applying a softmax over those two logits gives a calibrated comparison for this binary decision, not a global retrieval probability. The printed probability shows how strongly the model prefers true for a passage, which will be our re-ranking score. One pair is useful for debugging, but a real re-ranker must handle the whole shortlist in a single pass for speed and consistency. This snippet re-ranks the whole shortlist in one batched Hugging Face call by applying the same prompt shape to every PID and letting talk pad the batch so the model can process all candidates together. The model outputs first-step logits for each row, and label IDs is used across the batch, so we can extract the true versus false logits consistently. We then compute a log probability, or softmax score, for the true label for every passage, producing a numeric score per candidate. Sorting those scores creates ranked, a new candidate order that can differ from the keyword-heavy first stage. The printed output shows which passage moved to the top, and the score used to justify that move. Finally, we turn that re-ranking change into a tiny evaluation number that captures the user's relief when the right answer moves up. This code converts the re-ranking effect into a compact metric by marking P1 as the known relevant passage in crels, then reading old rank and new rank for that PID before and after re-ranking. We compute reciprocal rank, which is 1 over the rank of the first relevant result. So moving a relevant passage from rank 3 to rank 1 jumps its score significantly. The snippet prints the old and new positions and the resulting reciprocal rank change. In a larger experiment, the same idea scales to MRR or NDCG across many queries and judgments. The output shows that the relevant passage moved from a buried position to the first result. Mapping this toy flow into a real system is straightforward. Swap the small docs list for a BM25 shortlist from your index. Run the batched MonoT5 Reranker on GPU to meet latency needs, and log reciprocal rank or MRR on your user queries to measure impact. If you have judgments, you can fine-tune or calibrate thresholds on held-out queries so the Reranker matches product requirements. What this is: a sequence-to-sequence Reranker that treats relevance as a text-to-text choice and scores candidates by decoder preference. Use it when a cheap retriever gives a plausible shortlist, but the top few ranks must be precise for the user task. One caveat: it costs more compute, so keep it focused on short candidate lists. To extend this exact build, tune your first stage BM25 parameters, K1 and B, on your task, so the shortlist contains the most recoverable relevant passages before re-ranking. That one change often improves end-to-end MRR more than heavier re-ranker changes. If practical IR that improves what users see matters to you, subscribe and watch the IR videos.